My name is Julian, and this is for my INS final project. I'm here with.
My name is Ricky, and I'm just a step dummy.
Okay, yeah.
Let's do
Let's just tackle this optimization problem. So we have a garden supply company designing a cylindrical plastic compost bin that's going to contain 20 cubic feet of compost. Just stopping right here, what do you think this 20 feet is telling us?
Cool. I'm just gonna go ahead and write.
Yeah, go for it. Okay.
A garden supply cylindrical plastic compost bin to contain 20 feet of compost.
So what does that contain 20 feet telling us right there?
That's our constraint.
Yes. That is our constraint.
So, constraint. Nice one. 20 feet cube.
And then let's keep going from there. The bin will rest on the soil, so there's no bottom. There's a top, but there's no bottom.
Gotcha. So, I think what we should do is let me get that.
I have more colors in my pocket too. Yeah. Yeah, we'll leave that there. And it says the plastic size costs $2 per square foot. So we'll add a little cost tab over here. Cost, and we'll say sides equal $2 and top equals $3.
So $2 per square foot.
Mm-hmm.
$2 per square foot.
Alright.
So now I've determined.
Now we need to minimize. And then let's think about what this is saying. How do we minimize or maximize?
So we're gonna have to, I'm guessing, equal our constraints for doing variables, right?
Yeah. We're gonna have to create a function. Then once we get that function going, we're gonna have to take the derivative of the function and then set that equal to 0 to minimize. So what are some things we know about that cylinder just off of the start?
That the top part's gonna be more expensive, it's gonna be $3 per square foot. And pretty much the sides are gonna be $2 per foot square.
And then I will just add some things to your diagram. I really like it, but here's some key things. I'll just introduce a radius right here. We'll call it little r. And then I'll also introduce a height right here, h. So now we can start labeling and keep going from here. So, let's start at the basic. How do we get the volume of a cylinder?
So we need pi r squared.
Pi r squared, and then we're missing one thing. One of the variables labeled on the cylinder.
So it's equal to pi r squared. It's gonna be
That's the area, but the volume is one more thing.
volume is third, right?
No, squared still.
First line.
We're missing this h right here.
Oh, h that.
So we know our volume is pi r squared h. Now we can use the constraint, right?
So we make the constraint equals volume. So 20 equals h pi r squared.
And then we're trying to, okay, so the height really doesn't matter, but the radius is what matters because the top portion has a higher cost, and that cost changes depending on the radius of the top circle, right? So what expression or what variable are we trying to isolate right here?
We're trying to figure out R.
Actually the opposite. So we want a function for R, so we want to isolate H. Yeah.
So we just divide.
Mm-hmm. Alright, and then I want you to bear with me right now. This is where this problem gets kind of tricky, right? We have these labels, so I'm just going to get rid of this one right here. What would happen if we were to, from the center of this cylinder, slice it? What would happen if we were to just slice it and unroll it? What shape would we get? We get a rectangle. Exactly, and that's the biggest part about this problem. If we get a rectangle, what would our sides be equal to?
My sides will be equal to.
This is where it gets tricky.
2 inches per feet?
No,
it's
one of the variables just labeled.
Was it height and width? Height and width? No.
Here. So, one side will be height, yes.
Yes.
We know that just because the side of the rectangle will be our height. But let's think about this top part now. That's where it gets tricky. This top part is technically this circle unraveled, right? So now we have to think, okay, what's the area of that circle? How do we get, sorry, not the area. What's the circumference of that circle?
Gotcha. Just R squared.
Not exactly.
2R, right?
You're close. 2R is super close. You're missing one thing.
2R what? Something?
No. You're super close. Super close.
Oh, 2R pi.
2R pi. So we have 2R pi here. So then what would our area of this rectangle equal? Yeah. Times
H.
2R pi times H. So now we have our area expression of this rectangle that we kind of got from our, cylinder that we would be getting. So now we're going to come up with an expression for the top. And this is where this is really tricky too, because the areas come into play, but then the cost affects it. So now let's think of our cost, right? We know that to get the area of we have our area expression for the rectangle, and now we need to come up with an area expression for the top of the circle. Because that's what we're looking for. We're looking for the areas so that we can apply the cost to start minimizing. So we have one area. Now we need to think of this area, the top. What's the area of the circle?
There, the circle was pi r squared,
Pi r squared. Pi r squared.
R squared, yeah.
Pi r squared, h is the volume. Pi r squared is the area. So we have an area for the rectangle. We have an area for the top. We'll go area equals pi r squared. So now we're going to create a cost function because we're trying to minimize the cost, right? So I'll say this. Cost is equal to top area plus side area. I want you to try to fill in what you think it would be. Oh, sorry. There is one thing missing. We have to apply the cost, so the top is times 3. So if I rewrite this, it should be 3 times.
Yeah, because per foot, right?
Yeah, the top area plus 2 times the side area. So I want you to try to fill it out underneath it. You are super close. So I agree with your side area, but I don't agree with your top area.
Side. Oh.
Exactly. So now we have an expression for cost. Cost is going to be equal to 3 pi r squared plus 4 rh squared, or r pi h squared. Now we're going to get a little tricky, right? I'm going to move this over here just so it's closer to this, so it makes a little more sense. So I'm going to call this c of r, just like f of x, you know what I mean? C of r is equal to 3 pi r squared plus 4, I'm just multiplying it through now, r pi h, right? What does our h equal to?
23 pi squared.
Exactly, so now we're going to substitute this in. This is a really in-depth problem. This one is genuinely really tricky.
No, but it makes sense because of 2r, 2 pi.
Yeah.
That's the whole thing.
So how does this clean up now?
Just like keep going.
And then just before you write it over, remember how we rewrote these denominator fractions, so it was in the numerator. So just over here, I'll write it out, just so it's easier when we take the derivative. Or what do you think would happen? How can we rewrite this so it's a little easier if we wanted to take the derivative?
This one?
Yeah, this expression I completely agree with, but there's just another rewrite that could be a little easier. This is a hint.
ln.
Close, no ln, just a rewrite. Kind of like how we were doing this one.
Yeah, or 1/2.
So what can we do with this one?
So we're going to do just r-1?
Yeah, exactly. So I'll write it right here.
Gotcha.
CR is equal to
I was
3
thinking that, but I didn't know you could do that.
pi r squared plus 4, or 80 now.
80 feet cube.
80 times r to the negative 1. So now we have an expression for CR. The cost with respect to the radius, and here's our expression. So remember minimizing and maximizing now. So what do we need to do? We're almost there. But what do we need to do now to start to actually minimize this problem and optimize?
Wait, this is the constraint. So we
Nothing with the constraint. We've already factored in the constraint when we dealt with the height. So we need to take the derivative, remember? So we take the derivative and then we get C prime of r. Once we get C prime of r, we're gonna set it equal to 0, remember? And then that'll give us our critical points. So what would the derivative be of this expression? Let me get rid of this now. Hold up. You haven't taken the derivative yet.
Oh no, I'm thinking it. Oh,
Yeah, if you were to do that, that would just give you the points on, I guess, the R graph. You know what I mean?
This goes away, doesn't it?
No.
Last name.
Yeah. Nice.
Right. Well, I could put a 6 in an R, right? Or does that not count? It's negative.
Oh, that does not count, no. Here, this might actually help you though, if we go back to the previous rewrite. So try to move on from here.
I got you.
6 pi r minus 80 over r squared equals 0. R squared. R squared.
Oh. So much you can factor out.
It's much easier. Much easier than that. Just simple algebra. Here, this will help move you forward. Oh, you're good. If you need a break too, we can take a break. This will help you move forward. 6 pi r equals 80 over r squared. Because you can add it over. Try that now. That should help with isolating r. You need to sit too. We have chairs.
Sorry, I know mine somewhere else today.
You're good. You're good.
So we're trying to isolate the
Yeah. So what we can do to keep moving from here is we can multiply both sides by r squared now. Because you see, that'll cancel out the r squared here. And that'll give us this expression 6 pi. Oops. That'll give us the expression 6 pi r cubed equals 80. Now we can divide by 6 pi and we get the r cubed is equal to 80 over 6 pi. If we want, we can divide this by 3, simplify it. So I will. I'll just rewrite this as r cubed equals 40 over 3 pi, right? Completely valid. And then all we need to do now is clear this cube. So we have an expression now that r is equal to the cube root of 40 over 3 pi. So now we've come up with an expression for our r. So we're practically ready to solve this problem. So there is one more verification step if you wanted to do. I'm not asking just because I don't think that there's much of a need, but if you wanted to really verify that this was a minima, you would have to take the double derivative. So we take the derivative of, where is it? This expression. And then we would also do the same check and then figure out if it's a local minima or a local maxima. But I'll tell you that it's a local minima. So now we can go back to our initial CR, right? And plug everything in. We have R. So all we need to do now is plug in R's. Yeah. So I'm gonna start just erasing the work. I hope you don't mind. I'll just erase this portion because it's not really needed anymore. So I'll take it over here too because I know you're probably in a little bit of pain. Take a seat, relax. You're good, bro. All right. So our expression for CR goes from 3 pi r squared plus 80r to the negative. Now that turns into 3 pi times the cube root of 40 over 3 pi plus 80 over the cube root of 40 over 3 pi. And now this is the expression we have for the cost. If we were to go through and solve this, we would have values that we could quantify and then get costs for. So I'll do that right now, and it'll be quick. R is equal to square root 340 over 3 pi. What's up, Bobby?
Good morning.
This would equal to a value of 8.62. We also derived an expression for h, right? Where our h was equal to, oh shoot, we just deleted it, so let me rederive it. 20 is equal to pi r squared h. So 20 over pi r squared equals h. We know what r is, so let's plug this in now. So that h turns into 20 over pi times the cube root of 40 over 3 pi. So now let me pull out a calculator. This expression turns into 2.43. So we know that this height is equal to 2.43 feet. And where is it? The radius right here is equal to 8.62 feet. So now we can use this expression that we just derived and figure out how much this will cost. This CR expression. Huh? No, you're good. What do you think this CR, but what do you think this expression is gonna equal?
It's gonna equal the constraint 20 feet.
Like that. You said it's gonna equal the constraint?
Or at least give us dollar value.
It'll give us a dollar value. And how much do you think that'll be? Based off of the costs and what our sizes are. Just a rough estimate. I don't expect you to get it on the dot, you know what I mean? This is more just like a
It's like $25 on top. I'm say like 26.
$26 total, you think?
No, and then plus this times this side on the side, which is by 2, about like $31, $32.
31, 32. You're off by 4.
Huh?
So this will actually equal $74.10. $74.10. This because if we just chug through this, the top here.
It's it's radius because it's like squared.
Yeah, that square value makes it a
64.
lot
It's
more.
like it's like 60, almost 70. Yeah, that's crazy.
Oh, I'm so sorry. This is an 8. That wouldn't make any sense. We would have like the longest freaking. This is 1. I'm sorry, I wrote 8 for no reason. This should be 1. So
It should be a lot smaller.
yeah. So writing this expression now, we would say if we wanted to create a gardening supply cylinder, to minimize the amount of cost, we would need a height of 2.43 feet and a radius of 1.62 feet to get us our lowest possible value of $74. This one is a little different than what you guys did too, because I know you guys did a lot more maximizing problems and trying to maximize the amount of area or maximize the cost. But this is the flip side. Now we're trying to minimize. And it kind of changes the way you have to think about the problem. How do you feel about this? Any like questions or any like takeaways or anything like that?
It's just like you said, it's a little bit of the opposite. The constraint doesn't really give you much, just enough to kind of feed you, but you have to figure it all out.
Yeah, this one is a lot. I chose this one specifically because the constraint doesn't give you as much info as the other ones.
Mm-hmm.
You know, your constraint kind of told you how far to go, but this one is just like,
Yeah, it just tells you how much feed it is. That's it.
Yeah. So this is a cool one. You want to try an antiderivative problem? Do you need a second?
Yeah, let's do it.
Okay, cool. I'll get rid of this stuff, and then we'll slam an antiderivative problem.
Unless Javi wants to join it.
Bobby, you got it in me?
No, I'm okay. The best one I'll probably say do sigma.
Huh?
Sigma.
What do you mean sigma?
To do a problem like that to show everybody.
You can't do that problem doing sigma.
Oh.
You know what sigma means, right?
Yeah.
There's no way that you could add up everything.
Just because there's two different costs, two different variables.
It's okay though. This is a hard problem.
I'll say probably do one with the graphing one because I know they're probably gonna have that in their final.
Yeah.
That one's gonna be tricky.
For sure. Oh, those are good. For sure.
But I apologize if I interrupted you.
Oh,
You're
not
fine,
fine,
bro.
not at all, bro. The more the merrier, you know?
Well, I'll catch you guys later.
Yeah, I'll see you around, bro. It's a good problem. I really like that.
No, it is a good problem. It makes you think outside the box a little bit more. So, you gotta work for this a little bit harder, a little more.
Okay. Alrighty. Let's start general. I like starting general before we jump into more specific problems. And I won't do anything like super crazy with any antiderivatives.
She did give us a pretty crazy antiderivative.
Really?
Yeah. She had at least 4.
Okay. Then, did you go through the notation where it was like
But I think some of them were constants.
Let
when they're constants.
f
cancel out,
prime of s equal f of x, and then let f of s equal f prime of x? Did you learn about that? Where it's like kind of reversed? That's kind of like all that antiderivative is based off of, is that they're, all this is trying to say is that an antiderivative is the opposite of a derivative.
Yeah, it just stops.
Yeah, literally just the opposite. So, let's think about power rule. When we take a derivative, d to the dx of x to the n, what is the general formula for this? How does this end up looking?
You're gonna be dividing the x by x, or then whatever number it is.
Oh, I see. think this is derivatives. We're not antiderivatives.
Oh, it's derivative.
Yeah, we're still talking about
okay.
derivatives.
And then you go the n moves forward.
And move forward.
And then you say n minus 1.
N minus 1, yep. Okay, so that's our formula for a derivative. But now let's look at the antiderivative, f of s, of x to the n. Now think opposite.
This is gonna be n plus 1.
N plus 1, I agree with you. So coming over here, we'll have x, n plus 1,
Divided by n.
divided by,
X divided by n.
divided by n?
Yeah.
We're missing one thing. This is super close.
So n plus 1. Oh, n plus 1.
N plus 1.
Right, because it's the same thing top and bottom.
Yeah, same thing top and bottom. That's the difference between this. This is the starting minus 1. This is the incremented always.
Yeah.
So now that we've gotten over the general, we'll just hit you with like 3 quick problems. X is equal to 4. Find dx and big F of x. So what would the derivative of this equal?
4x3.
4x3. Easy. Now what would the antiderivative equal? This is where it gets trickier.
It's 5 divided by x and to the 5.
So say that one more time. x5 divided by
x5 divided by 5.
x5 divided by 5. Exactly. Now we'll get a little trickier. Let's go with 6x to the 7/8.
6, 8 to 7/8.
Yeah, so let's do derivative first.
So we're gonna do 1, fortunately. So we do that. Oh, that?
Yeah.
6, 60. Sorry.
It's good.
60, no, 6 times 7 is
You're good.
54, 63, no, yeah, x.
No,
And
it's
minus 1, so negative 1/8.
negative 1/8, yeah.
It's 42.
That's 42.
Yeah.
So we know that the
36,
derivative
because 30 times 3 is 36 times plus 6 is
30. Wait,
42.
6 times 5 is 30 plus 14 is 44.
You just add another 6.
Yeah. Okay.
It's 36, no, it's 36, and you add another 6.
Oh no, plus 12, 42.
42.
Yeah, you're right, you're right.
That's why they need
42 over 8
negative 1.
x to the negative 1/8. Good, very good.
You can make it smaller too.
Yeah, you could. Can't simplify.
Yeah.
Let's do the antiderivative now.
Cool. It's derivative. Give me a second.
You're good. Yeah. If you want to try it, here's a marker. I know that your back is killing you right now, though, so if you're just trying to chill.
It's my legs together.
Yeah.
I get like recognition. I get my second opinion on this.
Oh, nice.
I'm trying to avoid the surgery. Okay, let's do this. Sort of get that expression.
This is just a side note. I'm sorry to cut into your thinking,
I'm
but
sure.
this might help. If you ever get A over B over C, you could rewrite this as A times C over B. That might help.
You're exactly the ones that kill me here.
These ones are tricky. Antiderivatives are not easy.
It's just because of the fraction part, but you know, it's going forward.
Here, do you want me to walk you through this one? I'll give you a second fraction one and I'll show you how I like to do these ones.
Cool.
So we know that the n plus 1, right?
Yeah.
So we need to do 7/8. Oh my god.
There, take this one.
Thank you. So we need to figure out what 7/8 plus 1 is. That's going to turn into 7/8.
That was gonna be my questions. So
Eight
you're
eighths.
just always gonna add one, right?
You're always adding 1.
That's what I was thinking. Cause sometimes this is what tricks me out.
Yeah.
And we never did that.
These.
She just kind of expected us to know. So because it's n plus 1,
Mhm.
God.
I would always write
should've
this
just-
step out.
I should have just looked right there.
Yeah. So what is 7/8 plus 8/8 equal to?
15/8.
15/8. Yep. So now we know that we're going to be dealing with 15/8.
In the bottom.
So I'm going to rewrite it right here. 6x to the 7/8. So we know that it's going to be 15/8. So what I could write now is x to the 15/8. Because it's going to be to that power. And then we're still going to have that 6x.
Yeah.
But now we're going to be dividing by this. Divided by
15/8.
15/8. And that's why I brought this point right here. Because now we're going to have 6x to the 15/8 times 8/15.
Oh, cause you could switch it.
Mhm.
Gotcha. It's a division.
And then if this was 42, we add 6 more, that becomes 48. So then you get 48x to the 15/8 over 15. And that should be the derivative. We'll double check it right now.
That makes so much.
Or the antiderivative.
Dude, I was looking at these grade extensions this morning actually. Let me see the saves.
Nice. Perfect. This is exactly the answer. We could have simplified and divided by 3. Yeah. But no, you want.
I wasn't worried about that part.
Yeah.
I was more worried about you don't understand.
Here, just tackle this one then, and I won't give you something crazy. We'll
No,
do.
go ahead. No, give them to me, man.
Oh, I got you. Here.
I still need to get better at them. I need to understand them, you know?
5. This will be a nice one. We'll do it over here. 5x to the 4th. Check that one out. See how that turns into. Just find the antiderivative, yeah. Then we'll call it there. Boom. Yeah. Exactly.
Yeah. Give me some hard rock.
Alright, alright. How about this then? Over 4.
Full forward.
There we go. That's a challenging one. You caught me in that one. That was the easy one. Yeah. Nice. Nice. There it is, bro.
Yeah. She got nine. Keep adding.
Yeah, there it
Yeah,
is.
keep going.
So
Keep-
soon,
Give me add some constants in there or something, you know? And
soon
that's-
you're gonna learn that this f of x symbol, the capital F of x, is equal to this integral symbol, and then you'll start dealing with integrals.
I'm actually more used to seeing this.
Okay, cool.
Yeah.
I'll start writing it like this from now on. But you'll start getting some really cool integrals. Integral of sine of x dx, you know. This is opposite derivatives now. So if we took the derivative of sine, what would we get?